Good morning. So in numerical atmospheric modeling, we solve the fluid equations which describe the flow of the atmosphere. This is done by the part of the model known as the dynamical core. So this fluid solver should have certain properties. Properties that we're interested in would be conservation. This means that the numerical methods used are going to help us guarantee conservation of mass, energy, and so on. We'd like high order accuracy. This means we're going to get the right answer with fewer grid points, essentially. Geometric flexibility allows us to adapt the resolution of our grid to the problem we're trying to solve. And excellent scalability means we can take advantage of the increasingly parallel supercomputers that are coming online and get our simulations done more efficiently. So we'd like to satisfy these conditions if we can. The discontinuous Galerkin method, it's an algorithm for solving PDEs, gives us all of this, so we like it. It is rapidly gaining popularity, not only in this field, but actually in many areas as well. So a little bit about discontinuous Galerkin. This is a class of numerical methods for solving PDEs, specifically PDEs in this flux conservation form. So we've got here a solution U that we're trying to find, and this equation relates its time derivative to the divergence of some flux and some source terms. So just to give some intuition, if we're worried about maybe conservation of mass, U could be a density, a mass density, and then we'd be looking at the divergence of the flow. So is the flow pushing the matter together or spreading it apart? The discontinuous Galerkin is going to give us an approximate numerical solution to the true solution. This approximate solution lives on a computational grid. So I have an example here of a possible grid. We have the sphere as our simulation domain. We've broken it up into these little elements, the patches here. Each element can be mapped back to a kind of a reference computational element on which we have a grid. So we have several ways of choosing how we want to resolve our solution. We can choose how many grid points we have on each element. We can also choose how we distribute the elements. The solution is going to be discontinuous between neighboring elements. That's why it's called discontinuous Galerkin. And when we want to kind of get a global flow of information across the problem, we need to get that information connected back. And we do this by adding a term here that relates the boundary terms of each element to the boundary terms of its neighbor. And so you have nearest neighbor communications, which is good because this means you can scale efficiently. Now, whether you're going to use a discontinuous Galerkin method or a different method for your problem, you're going to run into this challenge when you do a three-dimensional atmosphere. This comes about because the atmosphere is very, very thin. It's about 1,000 times thinner than it is wide. So your vertical grid points are going to be super, super close together on the scale of the problem. This means that if you want to take time steps, you're going to be limited by the closest grid point spacing, which is going to be the vertical one. And you're going to be taking tiny, tiny time steps. It'll take a really long time for your simulation to get anywhere. The traditional way to get around this is to treat your horizontal directions and your vertical directions separately. So you can kind of split the equation into the two-dimensional horizontal part, the one-dimensional vertical part. You do the same thing with your time stepper, so you can take time steps using the horizontal component or time steps using the vertical component. An example of that would be strength splitting. What you get by doing this is the ability to use an implicit time stepper in the vertical direction. And without getting too technical, this means you can take much longer time steps while still being stable. So then you can get around this kind of very small grid point problem, a very closely spaced grid point problem. There's always a downside. Here we get some errors from these splitting. So if you were to do this in a discontinuous Galerkin method, we could kind of rewrite the terms I had on the previous slide in this way. We could have the x and y components of the divergence and the boundary communication kind of lumped together. And we could add the z components to make an effective source term. So this now looks like a two-dimensional discontinuous Galerkin formulation with a one-dimensional piece hiding in here. This is kind of like doing separation of variables on your PDE operator. So ideally, we would use discontinuous Galerkin for its nice properties, and we would use it with this dimensional split approach for the nice time stepping. But if you're going to do this, you'd really like to understand what sorts of errors are going to be brought in by this process. And this actually has not yet looked at for three-dimensional discontinuous Galerkin. So what we'd like to look at here is what are these errors that are introduced by the splitting? And we're going to, for now, just look at the operator splitting. So I'm not going to mess with a time stepper. I'm just going to kind of see what happens if I rewrite my right-hand side as a XY piece and a Z piece. So I can do some pen and paper work looking at the equations. And it seems like if I have a simple scenario where my grids are not too deformed, where my system is linear, I would actually expect the split and the unsplit to be equivalent. But the fully general case is not clear. We don't really know what to expect there. So what we'd like to do is kind of explore this question numerically. We're going to write a test code. We're going to do some experiments and see how the split and unsplit discontinuous Galerkin codes compare. We're going to start with a much simpler equation than the full fluid dynamics. We're going to use an advection equation. So what we're doing here is we're evolving some kind of tracer density in a specified velocity field UVW. So this means I'm not actually solving for the velocity. I'm writing down what the velocity is. I'm putting some tracer in this flow, and it just gets blown along. So this could be, you could think of this as being a pollutant or pollen or something in the air, and you want to see where it goes. All right, so the code we wrote, kind of starting from scratch, we have a three-dimensional discontinuous Galerkin code here. We use a three-dimensional Cartesian mesh, so this means our domain is going to be cube-like, and it's made up of lots of little elements, each of which is a cube. You stack them together to make a big domain. We support terrain-following coordinates, which I'll talk about later. We have both the full 3D discontinuous Galerkin and the split formulation, and as I said, the advection equation. For the experts, we're using a stability-preserving Runge-Kutta 3-time stepper, a Lax-Friedrichs numerical flux. We have periodic or no-flux boundary conditions, and we did not go into the limiting and positivity preservation side of things in this project. This code is in Fortran. It is parallelized using MPI between columns. So what I mean by this is as I partition my domain across my MPI processes, I do this partition in X and in Y, but I don't actually split it in Z. So here you can kind of see hopefully you can see the colors. So I split this domain into 8, so I have 4 by 2. So seen from the top, it looks like this. And then because I have to communicate this boundary data between neighbors, I need to communicate something between these MPI processes. And so these arrows kind of show what the network of communications is going to look like. So we have this code, and we'd like to know whether we wrote a good code. So we're going to do some tests on a very, very simple problem that we understand fairly well. So this kind of helps us to understand whether we're performing as expected. So this is a solid body rotation. What we're going to do is we're going to take kind of a spherical blob of our tracer, and we're going to put it in a rotating flow. This flow is such that it should rotate as a solid unit, and we expect that because it's centered in the flow, it will neither move nor deform. So it should still just look like a spherical Gaussian at all times. Any deviations from that are errors that come around from the numerical evolution. So here I'm showing, this is really a full three-dimensional problem, but I'm showing a slice through the middle. So you can see the contour lines of the tracer density and then the flow around. So we're going to do some tests to see the accuracy of our code. So the first of which I'm going to show here is the H convergence test. This is a measure of how your errors decrease as you increase the resolution bit specifically by increasing the number of elements. So I'm going to use more smaller elements. So here I have 8 elements per dimension, so 8 cubed elements total, 16, 32, 64. You can see the errors go down. With this order of discontinuous Galerkin method, I expect a 4th order convergence. That's the kind of gray line, and you can see we are parallel to that line. So that means we are performing as expected. And you can also see that the 3D and the split methods are very close to each other. So far, this is looking good. The other way we can test our accuracy is doing a so-called p-convergence test. So here, we keep the number of elements fixed, and we increase the resolution by adding more grid points to each element. So here I'm plotting the polynomial order within each element. So this increases as I increase the number of grid points. And again, the error goes down rapidly. In fact, it falls exponentially, as you can see on this log ln graph. And this is kind of expected from, say, a finite element scheme, which this is. Again, you can see the 3D and the split schemes agree. And the last thing I'd want to check is my parallelism working? So here I'm showing, well, okay, so let me say, what I would like to see is if I use n processors, I would like to see my code run n times faster. So what I'm plotting here is the speed up, how much faster it's going, versus the number of processors. This gray line is the ideal case where it's perfect scaling. So you can see I'm a little bit below that. And I attribute that to be due to the fact that the advection equation has effectively no computations going on. It's very, very cheap. And so I spend all my time moving data around. So I think I'm limited by that. As I increase the number of processors and I'm putting fewer elements on each MPI process, I have less data to communicate and move around. And so I'm actually approaching, again, the ideal case, which is why I'm actually scaling better than linearly in this regime. Here, when I'm only partially using a node, something is clearly not going quite right, but it's also not a realistic use case for the code, so I'm not too concerned. So quick recap. We have this code. We tested that it has the expected convergence behavior, the expected convergence behavior, the expected scaling. And we see so far consistency between the full 3D and the split ways of writing down discontinuous Galerkin. So let's now look at some more interesting numerical experiments. The first of which here is a deformational flow. This is a little difficult because it's a multi-scale problem. So you start with kind of this big scale Gaussian profile. And what you're going to do is you're going to put it in these vortices that are going to stretch it into something long and thin. And then you're going to reverse the direction of the vortices. And you're going to try to recreate the initial state. So I'm just going to play a movie because these is much easier to see than explain. So the vortices are stretching out the initial distribution into this long, thin ribbon. The vortices slow down. Now you're just pushing this across the grid. The vortices reverse. And you're going to try to recreate the initial state. Now, because you've turned this blob into a long, thin ribbon, it's actually much harder to resolve because it's a much smaller feature. So you're going to lose some information. And this is reflected. When you come back, you can see it's a little lumpy. It doesn't quite have the same shape. And this is information that you lost while it was all stretched out. So by comparing the final and the initial state, we can get a measure of the error. I plot here. So this is, again, H convergence. So I'm increasing the number of elements. The error goes down. Note that the convergence rate is now third order instead of fourth order. And this is because of this kind of multi-scale nature. It is no longer possible to get everything back out. I am plotting the 3D and the split here. They are exactly on top of each other, at least at the level of this graph. They do differ at several decimal places in, but the actual error from the problem dominates the error from, or the error between the two methods. The last case I'd like to show you is this kind of it's a test of your ability to resolve a flow through a deformed grid. So what we're doing is we have the blob of our tracer, and we're going to push it over this mountain. So we've all been outside, and we know this isn't a very good mountain, but we've got to start somewhere, right? So the mountain is going to affect the coordinates of our domain. They are going to, I'll show you in the next slide. And what we're going to see is how well we can resolve the tracer as it flows through this domain. So here's a cut, a vertical cut through that mountain. So it has this wavy profile. And the coordinates follow the terrain. So down here, they wave with the mountain, and then they kind of smooth out, and they become flat at the top. I don't know how to write equations or solve problems on these wavy coordinates. So what I'm going to do is I'm going to transform to a Cartesian set of coordinates where I know how to do math. Doing so is going to bring a metric in here. And I also have to transform the equation that I'm solving, this advection equation. But it turns out that the transformed advection equation actually has the same form. I just have to redefine cleverly my variables. So I have a new vertical coordinate, which is this one, zeta. I have a new conserved quantity. So I used to have the physical density, rho, of the tracer. And now it's weighted by the Jacobian. And then I have this new velocity that kind of couples all of the physical velocities together. So if I go to these new variables, I can evolve the same equation, so the code doesn't have to change. And I do want to emphasize, so we're not doing like real physical fluid dynamics here where you would expect the flow to react to the mountain. This is still an advection equation. So I'm just going to push my tracer over the mountain, and the test is, can it successfully evolve while the coordinates are wiggling under it? So here is the initial state. I have the mountain on my physical grid, and here's my computational grid. Here, there is no mountain, so the two coordinates agree. I'm going to evolve a little longer. I'm evolving in this space, and the metric means that all sorts of weird things are happening. My flow is going to do these wiggles. But if I map back to the physical space, I see that the blob is doing exactly what I expect. It just got pushed over to the right. And I'm going to keep pushing it, and I recover the nice state in both frames. I can compare the final and initial to get, again, an error estimate. I see, once again, that we have the third order accuracy. This time, the order was reduced not because of the multiscale, but because some of the resolution effectively goes into resolving the Jacobian instead of resolving the solution. By the Jacobian, I mean the coordinate transformation. The 3D and the split methods, again, agree to within the precision of the graph. They are slightly different. So to conclude, we set out to assess the impact of dimensional splitting errors in a three-dimensional discontinuous Galerkin method. To do this, we developed an MPI parallel 3D advection code. This code we showed has the expected scaling and convergence. And it's going to be a good framework for future extensions. I think Ram has all sorts of ideas for what he's going to do. And then we use this code to compare the 3D and dimension split methods using several different test cases. We found them to be virtually identical in performance. This is promising for using this split scheme in 3D atmospheric models. But before we can really be confident with that, we'd want to continue these tests and try nonlinear equations, maybe more aggressive coordinate transformations, and make sure that the similarity between the two methods carries through to more general problems. So I guess the immediate next step is to take the code and extend it from the advection equation to the non-hydrostatic Euler equations and see what happens. To conclude, I'd like to thank Ram for lots of good discussions about discontinuous Galerkin and a good project, and AJ, Sylvia, Kathy, and everyone who has made this smooth, fun summer. Thank you.